All right, so in this example, we've done it two slightly different ways, and seemingly we've come up with two slightly different answers, which means we must be able to demonstrate that those are in fact equivalent answers. And so let's see how we might be able to do that. Well, let's come to the first of our two answers. So there we had 4 times the natural log of the absolute value of a quarter x minus 3 plus c. And so let's deal with that coefficient of x, that quarter. Let's factor that out of the argument of the logarithm. We can write that as 4 times the natural log of the absolute value of a quarter times x, and then we pull the quarter out of 3, that would be 3 times 4, which is 12, plus c. And you can always multiply it back into check. A quarter times x minus a quarter times 12 does give us back the original argument. And now we can recall that, well, logarithms have a bunch of different properties, but one of them tells us that the logarithm of a product can be written as a sum. So I can write this as 4 times the natural log of the absolute value of a quarter plus the natural log of the absolute value of x minus 12 plus c. And if that looks familiar, it should, because that's the expression we got from our second approach to evaluating this integral. So I do get 4 times the natural log of the absolute value of x minus 12. I'm just going to switch around the order of these terms here. 4 times that. But I seem to get something extra. I get 4 times the natural log of the absolute value of a quarter plus c, which I didn't have when I used that second approach to the integration. So because I've got this extra bit here, does that mean that I somehow did something wrong one way or the other? Well, no, because again, this constant integration, although it's pretty innocuous, it's pretty easy to kind of just treat it as just this annoying thing we have to tack on to all these indefinite integrals, it does play a role. Again, it represents any real number. And we've already talked about how we can multiply or divide it by a constant, and it doesn't change the fact that it's still any real number. And we've talked about how we can add 2 arbitrary constants or subtract them, and they still just combine into a single arbitrary constant. But the same would be true here. 4 times the natural log of a quarter, well, that's some constant, some horrible irrational number. But if c represents any real number, and we add even a bit of a nasty constant to it, that still represents any real number. So we can absorb those together, and then that would simply give us 4 times the natural log of the absolute value of x minus 12 plus a new arbitrary constant. Again, usually you'll just see the symbol c used again, but technically this is now the original c plus this constant. So if you wanted to represent that as c1 or d or whatever you like, that's also a reasonable thing to do. So we can absorb that constant term into the arbitrary constant. And that's why, in fact, those are equivalent answers. All right. So there's linear composition and some things to bear in mind when you're using that result about how to apply the constant integrals, or the common integrals rather, to a case of linear composition. Which I guess raises the next natural question. If we're able to figure out a result for linear composition, what about other forms of composition? And I guess if linear composition is the simplest instance of a composite function, quadratic composition would be the next simplest. So let's think about that for a little bit. So could we obtain a similar result? for quadratic composition, instead of linear composition. So in other words, here we're talking about an integral that would be of the form integral of some function whose integral we would know. Again, that would be on our list of common integrals. So it would be f of not a linear function now, but some quadratic function, ax squared plus bx plus c. And well, again, let's take a simple example and let's think that through. So let's try to go back to the first example we did today. Instead of doing a linear composition, let's do a pretty simple quadratic composition. We don't necessarily need both a quadratic term and a linear term. So let's get rid of the linear term. Of course, we need the quadratic one in there, or else it's not quadratic composition at all. So let's think about the integral of 2x squared minus 3 to the 60. And again, our hope is that we can relate this back to the corresponding common integral. So again, although you've already got it in your notes for today, I'll just write it down here. We're comparing this to x to the power of 60, or the integral of x to the power of 60, which of course is x to the 61 divided by 61 plus c. So we're going to kind of do all of this again from scratch. We're going to need to make a guess here. And if there's going to be a result here that we can make use of, then we're going to hope that however this integral works, that it follows something along the lines of that common integral. So just like we did for linear composition, we're going to guess that the integral of 2x squared minus 3 to the 60 is hopefully going to be something close to 2x squared minus 3 to the 61 divided by 61 plus c. But the only way we're going to know if that's close is by checking, by differentiating. So let's see, we take this result and we differentiate it. What do we guess? Well, again, we need the chain rule for the numerator there. So we'll get 61 times 2x squared minus 3 to the 60 times the derivative of the inside function. The derivative of 2x squared minus 3 is 4x. And that'll be divided by 61. And of course, we add on the 0, the derivative of the constant of integration. So the 61s cancel, just like they did in our first example today. But now we've got a bit more left over. We've got a 4 times x times 2x minus 3 to the 60. So again, that tells us that our guess is not correct, because this is not our original integrand. But we've got a bigger problem this time. Because whereas for our first example, and in fact for all of the linear composition examples, we realized that we were only off by a constant, by whatever the coefficient of x was. In this case, well, yeah, we're off by a constant, but also by a factor of x. And the problem with that is that we can't resolve that just by factoring out of the integral. Because yes, we can factor constants out of the integral, but we can't factor variables out. So this would tell us that the integral of 4 times x times 2x minus 3 to the 60, that's equal to our guess. But because at best we could factor out the 4 and figure out the integral of x times 2x squared minus 3 to the 60, that still doesn't give us any indication what the integral of 2x squared minus 3 to the 60 on its own would be. So we have no way to use this to obtain the integral that we're actually after, because we can't factor variables outside an integral. And so in fact, immediately then, that tells us that this isn't going to work. Because with any instance of quadratic composition, when we check by differentiating, we're going to have more than just a constant in the difference. And if it doesn't work for quadratic composition, then certainly any higher polynomial composition, cubic composition, or quadratic or quartic composition or anything, that's not going to work. Nor would it work if we replaced x with a trigonometric function or an exponential function or anything else. So unfortunately, no. Beyond linear composition, we don't have a nice pattern that we can rely on in order to work out the integrals of those composite functions. So sadly, no simple pattern exists beyond linear composition for the purposes of integration. So what are we going to do then? How would we work out the integral of 2x squared minus 3 to the 60 then? Or the integral of any other composite function where it isn't just linear composition? And going back to the broader scenario, what about products and quotients, where we can't straightforwardly rewrite them so that they don't involve products or don't involve quotients? There's clearly a huge number of integrals here that we can't integrate, not based on the elementary techniques that we've introduced here in section 1.1. And so this is what we're going to spend a lot of Math 1001 talking about, are different techniques which will target specific forms of integrals. So if integrals look like such and such a thing, we're going to come up with a technique that may let us evaluate those types of integrals. And then we're going to come up with a different technique for a different form. What that means is that by the time we finish Math 1001, we're not going to be able to integrate absolutely every function that exists, because we're not going to be able to go through every possible form that the integrand might appear in. And in fact, as we'll discover, there are lots of integrals, even some very simple integrals, that have no way to evaluate them whatsoever. And that's different from Math 1000, where by the end of Math 1000, basically, we could differentiate any function that we wanted. But that's the reality of higher mathematics. There isn't always an answer, and certainly not always a relatively simple answer to a given problem. That's one of the reasons why there is lots to investigate and explore and learn about as you move farther along in your mathematics education. But this is a pretty good start. This takes us to the point where we can now integrate any elementary integral, and we can now integrate any instance where at least we have linear composition, and a handful of integrals that do involve products or quotients or other types of composition if we can rewrite them.